Hello class and welcome back to Physical Geology. Today I'm going to go over the Structures Lab, and I have the whole lab actually here on Canvas, but you can't write on it, so you should or you'll need to download the PDF of the lab, and I've already done that. Yeah, so here it is, and you can see you want to make sure you put your name in there. This first section here deals with strike and dip, and simply call it the attitude. So basically the key thing to strike and dip is that strike is going to be this longer line of strike, and it's really a compass direction. So for example, the strike of these sedimentary beds, these tilted or inclined sedimentary beds here, note that we got a north arrow here. So the strike line is an imaginary horizontal line on the geologic surface. And in this case, it's paralleling the water surface, right? So if the water level will go up higher, it would make an imaginary horizontal line, right? We would want to measure that orientation of that imaginary line with respect to north, right? So if we had a protractor here, we can measure that this is going to be maybe, let's say it's about 50 degrees. So the angle from north to this strike line would be 50 degrees to the east. Remember, the right is east, the left is west. So the strike of this line, we'd say it's north 50 degrees east. And then dip is always perpendicular to strike, or strike is always perpendicular to dip, right? So in this case, the dip is the angle of inclination, right? And so in this case, it's 30 degrees. Obviously on a map, it's a planar two-dimensional surface, so you really can't show that third dimension. So the way we depict it is by saying that it's inclined by 30 degrees right there, right? And then here's a little strike and dip symbol they're talking about there. So kind of other ways to visualize it here. Here we have the back of a chair rest. So an imaginary horizontal line would be the strike line, and then it's inclined steeply down in this direction here. If it's horizontal, we use a special symbol here for horizontal strata. Kind of like a bullseye symbol. But if it's vertical strata, we use sort of this, again, the strike line, but then see it's sort of dipping in both directions. That would be for 90-degree dip. And here it's a pretty steep dip. And so here we drip some water down. We see it's going straight down due to gravity. So strike is going to be perpendicular to that dip direction, right? So it's a little bit about strike and dip. So on this first part here, you will need a protractor. In fact, one thing you could probably do is we'll do a line here. So what I would do, I would draw a line along that strike, right? And then I'm going to grab it and I'm going to put it over here. And when I put it over here, well, there's my line. And if I can imagine where it's going, so if that's 0, remember I'm counting 10. In fact, let's zoom in a little bit here so we can see it better. So there's 0. I have 10, 20, 30, 40, right? So 0, 10, 20, 30, 40. This is going about 40 degrees. So it's trending north, 10, 20, 30, 40 degrees west. So you say the strike is, so here you'd say it's north 40 west, right? And then the dip, it tells you right there, it's 24 degrees. But note that it's inclined in this direction to the southwest. So you'd say SW. And that's another good point to make here is by convention, if you see north first, then the angle, then the compass direction, east or west, that's always going to be strike. So by convention, strike has north first, the angle then whether you're east or west. Whereas dip, by convention, will always show the inclination first, then the direction, southwest, northwest, northeast, whatever, right? Go ahead and do these next 3 here. Again, doing the same thing. Draw a line there, bring it over here to this compass rose here, and figure out the strike. And then obviously the dip direction dip is telling you, is given to you right there. And then you'll do the same thing with this case here. In this case, they want you to figure out the strike here. Remember, strike is always parallel to the geologic context as well, right? So another reason it's important is if you don't see a strike and dip symbol, you know that the strike line will always be parallel to the geologic context. So that would be the strike line. In this case, they're telling you it's dipping in this direction there, right? So you would have a strike and dip symbol like that. And then I think they want you to draw a big arrow to show which way. Like for the example here, you can show they're all dipping in this direction, right? You could draw a big arrow like that. So to indicate the direction of dip. All right, so that's pretty straightforward for the strike and dip there. I want to get a little bit into geologic maps here, right? So the geologic map, we need special symbols, right? We'll have different letters to pick different units. Like Q is for quaternary, right? That's very recent for geologic time. If you had K is for Cretaceous, right? P is for Permian. So you'll see, I do have a figure down here that gives us some of those symbols, right? So you can see P is Permian, kind of a double P is Pennsylvanian. Where's Q for there's Quaternary, right? K for Cretaceous. So those are different symbols we use on the geologic map. And again, we'll have the strike and dip symbols in here for horizontal beds, vertical strata, strike and dip here. Also for folds, anticlines, synclines, faults, and some other features there. So that's an important figure to keep in mind. So this talks a little bit about geologic maps here. We'll look at a couple maps as we go along here. So I'll make a couple of bullet points about strike. And actually, one important thing we talk about here is this rule of V. And whenever a stream valley cuts into a geologic contact, you're going to get a characteristic V shape that will form. And that closed end of the V always points in the direction of dip, right? Because some maps will not give you the dip direction here, right? So here we have a picture of some sort of structure here, but you can see that there's a contact between this. It looks like a sandstone and a shale here, and then another sandstone here, so a thin shale. You see the little beds of shale there. And you can see little rivulets or little streams have come across here and eroded this contact to make a V shape, right? And note that the V is pointing toward the right. I guess if north is this way, it's pointing toward the south. So this is dipping south. Remember, the contact is parallel to the strike line is parallel to the contact, right? And the dip is perpendicular, so it's dipping south, right? So that's how we can use the rule of V's. And so we'll come back to this in a second here because I just want to point out a figure I have here. So here's a map, and these little V's, there's supposed to be a little creek that's flowing down through here, right? And you can see the V's are pointing, in this case, on the right side, they're pointing toward the left, on the left side here, and on the right side, they're pointing toward the right. So to draw your strike and dip symbol here, you would draw your line here. So remember the strike is going to be parallel to the geologic contact. So you could draw another one here, parallel to the contacts on both sides. But the dip direction here, it's telling me it's dipping one way. Here it's telling me it's dipping the other. So I'll let you kind of figure that one out. Also for this figure here, they're going to want you to complete the cross section here. Let's go ahead and figure this one out. Since the V is pointing to the right here, this is dipping in this direction there, right? So then we can say, well, the contact between this Devonian shale here and the Silurian sandstone, it's inclined toward the right side or the east. So I'm going to draw an inclination going there. And then the contact between the Silurian sandstone and the Ordovician limestone, this blue and yellow unit, I can see it's also inclined in this direction there, right? And then now your job will be to figure out what's going on this side here, right? And you'll see there's going to be some geologic structure that forms there. This next part on deformation, I have two block models I want you to look at. And you're going to have to look at these on our Canvas course page because it's hard to put them here on the PDF file. And I want you to make two different sketches of this block diagram. So if we go over here to our Canvas course page, you see I have the block models here. So we'll click on this guy. It's going to load up, and you can expand it here. And you can move it around. And as we move it around, note that there's this notch. This notch represents a stream. So a very steep stream and a more gentle stream, right? So that's like stream valley here. And then one of the questions I'm going to ask you is I'm going to ask you about the orientation. What's the dip direction? Estimate the degrees of dip. And then I want you to look at the top of this thing, and I want you to see this dark stratum, right? And you can see it's back over here. And I want you to compare it to this figure here, figure 6.6. And I want you to tell me, does it resemble block A, block B, block C, block D, block E, or block F? So take a look at this, and you'll have to answer those questions. So if we go back here, you'll do the sketches, and then what's the orientation of the strata? I guess you do steeply, gently, or horizontal, and then tell me which of those block models it fits. Then you'll do the same thing for block model 2. And so block model 2 is this one here. So I'll let you look at this one. You can expand this one, do the same thing. This one's also obviously dipping at some degree here, but do the same thing for block model 2. And then this question 3 is you're completing this, and we've already done that already. So that's kind of finishing off there. Then I do this in lecture about stress and strain. So two types of strain here are brittle and ductile deformation. Know the difference between those. And then here for ductile deformation, it's going to result in this folding. You'll have this kind of U-shape fold, kind of a trough-like fold called a syncline, or an arching fold called an anticline. The syncline is folded toward the earth, with the earth, so it's called syn with the earth. And then the anticline is folded away from the earth, so it's called anti, or away from the earth. That's where the terms come from. But one important thing is that there's going to be an axial plane, right? So an axial plane is an imaginary plane that bisects the fold at the inflection point, where it changes from one dip direction to the other dip direction. And in fact, at the axial plane, the strata here are horizontal. So you could put one of those bullseye symbols right there for horizontal strike and dip, and also here as well for synclines or anticlines. For a symmetrical fold, because these are symmetrical, for symmetrical folds, note that I just see parallel strata on both sides of the axial plane. I don't see the fold on the surface, and that's kind of true for this little block diagram. Note that there is a fold here, but we don't see it on the map. So this is going to be some sort of symmetrical fold. If I were to see the fold on the map, then that fold is said to be plunging. And a plunging fold is going to have this hinge line. So the hinge line is basically like the door hinge. You know, imagine there's 1, 2, 3 doors here. The red door, this brownish door, and the gray door, right? And each of these will have their own hinge line, right? And so if the horizontal hinge line, it's a symmetrical fold. But if the hinge line is plunging or dipping or inclined, then it's going to be a plunging fold. And note that for the plunging fold, sure enough, we see the fold on the geologic map. This is important because there's a question later on about plunging fold, symmetrical folds, right? All right, so it's a little bit about folds, and I guess I talk about them in here. And there's some special folds, and I think there's even a picture showing you that box fold and fault bend folds, right, where there's some faulting going on there. Overturned folds. Sometimes these overturned folds are called recumbent. There it is, which are kind of lazy folds. They're kind of lying down. In other words, the axial plane is lying horizontally. All right, so then for this exercise 6.4, you're going to identify which one's the anticline, which one's the syncline. You can just write it there. Then you're going to draw some strike and dip symbols on here, right? Draw some strike and dip symbols to show the orientation. Remember, the strike is always parallel to the geologic contacts, right? And then the plane, and then you can answer question 3. And then, yeah, so this is pretty straightforward. You will be able to answer that one. And again, that's referring to these two, this figure 612 up here. And then all this is figured as 612 up in there. And then for question 11, there's a series of pictures you're going to look at here for different types of folds. This is in Death Valley right in here. That's one of the ones I talked about already. Here's another fold in here. So what you want to do, you want to compare these photos with the figures we have up here. Probably most likely that figure, and then there's some folds up in here, right, that we have. So compare it to those there. And then to answer that question, I didn't leave you any space to write on the photo here, but you need to fill out this table. For example, photo A, that looks like a recumbent or I call it recumbent, but overturned fold, but a recumbent fold is what I would call it. So you would say for letter A, the type of fold is recumbent. I guess you'd put it over here, recumbent. But then what type of deformation? So since it's folded, they're pretty much all going to be ductile for the folds, right? And then try to figure out the angle of the axial plane. If the plane has any curvature, some may not, so you might have to leave. We'll see what you can answer on that one. And then whether it's symmetrical or not, right? So these look pretty symmetrical on both sides. These do not, right? So try to kind of figure that one out there. But mostly make sure you answer the type of fold. And obviously they're all going to be ductile for the strain, the deformation. This next part deals with domes and well, actually I call them structural domes and structural basins. The structural dome resembles an anticline. The structural basin resembles a syncline, right? But the key thing is that for remember when you're drawing strike and dip symbols here, the strike will always be parallel to the contacts there. Always parallel to the contacts. And then you can see that the dip direction here, everything's dipping toward the center, right? So do the similar thing for the dome, because they're going to want you to do that for them. Draw several strike and dip symbols to kind of get that in, just sort of get yourself oriented on that structural dome or basin. And then there's going to be a question here about the Black Hills in South Dakota here, right? So you'll take a look at that and see if you can answer the questions. Really, this is question number 4 there. All right, so brittle deformation, right, for faults. So the same idea here, we're looking at some different faults. And in this case, remember there's a hanging wall and a footwall. So put either HW, FW in the appropriate boxes here. They also want you to draw some arrows, right? Along the fault plane, draw arrows. For example, and the way to figure it out is there's these marker beds. Like this bed and this bed were once continuous, but this block has slid down, right? So if you were to draw an arrow, you would say that block is sliding down, right? You can do half arrows, and this block is sliding up relative to that one, right? So you would want to show the arrows on your faults there. And then again, you're going to have to draw some arrows in these bubbles. Make sure you use your tools up here. Pretty straightforward here. And then again, for question 9, same idea. You have a series of pictures. You're going to identify the type of faults, fault angle, fault type, tectonic settings. So, yeah, so it's either going to be reverse fault, reverse or thrust, normal or strike slip, right? So some of them could be strike slip faults. Try to estimate the angle, right? So this is going to be a vertical angle here for this fault here. But here you would try to measure this angle right there. So if you imagine some horizontal line and then the angle down to that surface, right? This is going to be a vertical one because this is kind of a strike slip fault right in there. And if it is a strike slip fault, is it right lateral or left lateral? That's another important thing to determine. Right lateral versus left lateral. And I think it mentions that over here with, right or left lateral. So make sure you can answer those questions. And again, you're going to fill out, and I guess for view, what they want to do, so this is, actually, that's a good question. So this question view is, so this is a map view because you're looking from above down onto the ground. This is a cross section. You're looking at a side of a hill here, right? This is a map view, right? Here's a cross section. This is a map view, and here's another cross section. So cross section is a kind of a profile sideways view, and or if you're looking from the sky down onto the map or onto the ground, we call that map view. So I guess that's what they mean by the view, right? And then work in the 3-dimension. Oh yeah, so this is going to probably be the more difficult problem you may have. You'll probably have to print this page and do it with pen and paper, right? Pencil and paper. I guess you could try to do the drawing tool, and we should probably use a thinner point here. Because what they're going to want you to do here is to show the geologic structure. So one thing, in fact, let's use black for so we have this fault here, right? And so the fault should be pretty continuous or linear through here, right? So there's our fault. And note that this block has moved down, right? And this block has moved up. So you'll have to determine what type of fault that is, right? Where this block slides down relative to that block. And well, I'll tell you right now, this is a normal fault. And the reason I want to point out, because I want you to use some symbols to depict the normal fault. So if we go back up here to our geologic symbols, we'll see that, yeah, up and down. Usually we use up and down for normal faults. And so up would be the side that's being pushed up. Down would be the block that's sliding down, right? So let's go back down there. So you would write, so this side, we'll put a U there for up and the D here for down, right? Something like that. You know, when I was in college, we had another symbol we used for normal faults. We would draw the dip direction, because it's dipping in this direction, and then we'd put a little ball here, like a heavy weight. And so that also indicates that this is sliding, this side of the fault is sliding down, right? So a little dip direction, little ball on there, or weight that causes this side, you know, to show that the side on the right has dropped down. All right, so then when we go back to our drawing tool, let's go back to our line. Now they're going to want you to show the geology, right? And so it's pretty simple here. These should be all, looks like they're all horizontal strata, right? The strike and dip symbol. In fact, you could even put that let's do back to our freehand tool here. So the strike of this would be that kind of that bullseye, right? Horizontal strata. Then we see that, oh wait, I didn't do this unit down here. Back to the line. There's one more unit. You want to show all the units here on all three sides, right? So don't worry about coloring them, but as long as you show the contacts on the side here. When you get to letter B here, these are the sort of engineering symbols. This is supposed to be like an arrow, this is the feathers of an arrow, which means that this block is moving away from you. It's moving that way, right? This block, oops. So if we could draw an arrow here, that block is moving this way. Let's put the fault in here, right? And then this guy's moving toward you, right? So that's some sort of strike slip fault. So go ahead and do the geology on the side. Again, it's going to be pretty horizontal strata here, right? This is a thrust fault for letter C. So go back and look at your symbols for thrust faults. So when you draw your fault in here, you're going to have to draw the special symbols to depict the thrust fault or reverse fault. This is some sort of syncline, right? And so one tricky thing about the syncline is the strata on the side are going to be horizontal, but you're going to have to show all the contacts back up over here, something like that, right? And then I think they want you to add the axial plane in here as well, right? To show the axial, and then maybe add some strike and dip symbols in here, because this one is, remember, the strike is parallel to the contact, but for a syncline, they're dipping. Whoops, if I can get it in there. We want to show a little dip. It's not letting me do it, but you want to show a little dip direction going toward the center there. So I'll let you work on that one there. Yeah, so you want to fill in, oh, they also want you to add hanging wall and footwall for any of the faults there. Yeah, and also the youngest and oldest sedimentary layers. And then for letter D, use what you've learned to complete the block diagrams above, from completing these diagrams, but to construct the block model in figure 10.8, which is the next page. The block should have 4 layers, and you should show an anticline, right? You're going to do it on this figure here. So to do that, you're going to have something like this, but make it an anticline, right? And then show your geology there. So I'll let you work on that one. And then this last part is an exercise on Google Earth. Oh yeah, the goosenecks of San Juan here, right? So I've actually rafted this river. I spent 7 days on this river about 3 years ago. And there was this rapid called Government Falls. Scary, but I made it. And I was captaining a raft too, so I had everybody's gear with me. But I survived. All right, so what are they asking us for this first question? So stop one brings you to Canyon National Park. Describe the orientation of the strata, right? So here we can see the rock layers of strata. Are they dipping steeply, dipping gently, or are they horizontal? I'll let you answer that question. And then are the semi-strata the same thickness, right? So are they the same thickness? No. So one thing about differential weathering, and we did a little bit of this in our weathering activities, the more resistant rock, like sandstones or limestones, usually form cliffs. So those are more resistant, whereas shale, because remember in the lithification process, shale has burial compaction, but really no cementation. Because remember you have to have pores or porosity for the cement to get in there to glue the rock together. But shale and mudstone, to that effect, really rely just on the burial and compaction. So over time, when this stuff gets exposed, it kind of expands a little bit and it crumbles more easily, right? So the slopes are going to be the shale layers, right? So the cliff faces are usually the limestones or the sandstones, the stuff that's been cemented, lithified well, and then the shales will be the slopes. So probably some sandstone, shale, more shale, then some sandstone, right? So go ahead, you can answer that question there about the different thicknesses. Tectonic activity for letter C here. This area, well, I mean, most of these are marine sands and shales that were underwater. So obviously there's been, this whole Colorado Plateau has been tectonically uplifted. In geology, we call mountain building events, we call them orogenesis. Oro in Greek means mountain, and genesis is birth of a mountain. So an orogenesis or an orogeny, uplift, exposure of a mountain. And in this case, we call it the laramide. The laramide orogeny is what's really responsible for this whole uplift of the Colorado Plateau. You can look up the laramide orogeny, named after Laramie, Wyoming. That's one of the type locations. All right, as we go down here, then now let's look at stop 2. And so on the Google Earth, you can see if you hit this button here on the side, let's move this over a little bit, it'll take you to the menu, and you can see stop 2 Mexican hat. Then you got to double click it. Yeah, there we go. Oh, and that's still the same San Juan River. And so they want you to kind of look at what's going on with the geology along this yellow line here, right? So let's look at the orientation of the rocks along the yellow line. What is the orientation of sedimentary rocks on the western, central, and eastern parts? So if we look at the western, so we're looking, I'm not sure if we're looking north or not here. Oh, here's north. Yeah, so we're pretty much looking north in that direction. So the west side would be this side over here. So let's zoom in on this side here. And these strata, oh, look at that. This is like that picture I had earlier. See the rule of V? The rule of V. So the contacts, so strike is going north, and this is dipping toward the left or the west, right? So you see the rule of V's? That's for the western part, right? Let's zoom out. Zoom in here to the center, and probably somewhere where there's some erosion where you can see what's going on here. Like right in here, see if you can figure out what's going on there. And then do the same thing over here on the eastern part, which is going to be, oh, look at that. Yeah, this is where you want to look right here. So go ahead and answer the questions there for the Mexican Hat region. In fact, the San Juan River goes right near this area. And that's some of the stops we actually did on our rafting trip. And then finally for 3A, we're going to Spanish Peaks, Colorado here. Well, if you've lost your place like I just did, all you have to do is go back to here. Click on this again. It'll reopen it. And then we'll do that back arrow. And then we'll go to stop A for Spanish Peaks, Colorado here. So they say it's supposed to be a batholith, but I think they're individual plutons. Maybe these two plutons. Remember, a batholith covers more than 100 square or 100 kilometer square area, and it's many individual plutons that are coalesced to form this larger batholith. So these are ancient batholith granitic rock that are exposed to the surface. Look at 3B. What is this feature? I guess they want us to go to 3B. Let's do 3B here. So it's a very long, linear. This is actually an igneous rock. There's another one back over here. There's several in here. So remember when this is the magma chamber. There was magma, and the magma was shooting what are those intrusions that are either discordant or concordant intrusions into the surrounding country rock? Because remember the batholith, bathos means deep and lith is stone. So this rock was once deep and it was magma and it was shooting these intrusions, right? So see if you can figure out what these intrusions are. Yeah, that shoot out. You can see there's a bunch of them that are coming out. Looks like they're mostly on this west side over here that are coming out of the from those batholith. Yeah, I see 2, 3 in there. So go ahead and answer those questions regarding the Spanish peaks there, right? And I think that's it. All right. Well, good luck and let me know if you have any questions.